You get Xavier. I good day, but it's still very here. I would never have. What was Mousy Johnson? Less mouse.
Okay, quiz is tomorrow. I just want to run through a couple of things and then have you guys continue practicing. So there's going to be 5 convergence tests that we need to be responsible for. I have them up on the board there. You got nth term test, geometric series test, p-series, integral test, and telescoping series. Okay. Let me run through each of the details from each of the tests and see if you guys have any questions. So first off, nth term tests. I would typically say that this is a good test to start off with, unless it's obvious that it's geometric series or if it's p-series. Those are easy to spot. If it's easy to spot, then I would say just jump to that. Don't have to do nth term test. But in the larger scheme of things, especially when we start introducing limit comparison and all the others, sometimes nth term test is a good way to just quickly see if we can say it diverges right before we commit to something that's more involved and complicated like limit comparison test. But I think for our purposes, it's like, if it doesn't look like geometric series or p-series, we typically can just go directly into nth term test. Remember that nth term test is only a test for divergence. Okay, you show that the limit as n approaches infinity, a base of n does not equal to 0. So it could be equal to 1/4 or 2 or 8 or infinity. All those are conditions to show that the limit doesn't equal to 0, and therefore you can just quickly say that the series diverges by nth term test. Okay. The only thing we got to be careful about with nth term test is that if the limit does equal to 0, we cannot say that the series converges. At best, we can say that the series may converge, but could also diverge. So it's kind of like this gray area that is not a very strong argument to say that this converges. So we have to basically look at a different test. Nth term test is not going to be a good enough test to show if the series is converging or diverging, because this is kind of like a gray area if you see equal to 0. Okay, so remember, nth term test is a good test to use, but it's only a test for divergence. Next up, geometric series test. This is going to be anything that involves like exponents. You're going to see some problems on the quiz review where things look out of place, like negative exponents all over the place. And sometimes you want to kind of, that's indicating that, okay, if I can rearrange it, maybe I can get it into a common ratio, showing me a common ratio. If I can get a common ratio raised to the nth power, then I can spot my ratio, my common ratio, and decide whether I have a converging or diverging series. So in this case, this is already set up very cleanly for us. My common ratio is E over 3. E is around 2.7. 2.7 over 3 is clearly less than 1. So this series would converge. And then if it converges, then I expect you to find the sum for geometric series. So you're going to find your A sub 1, you're going to find your R, plug it in to your sum formula, and then represent your sum. Okay. No calculator tomorrow, so if you leave your sum in unsimplified form, that's fine. Questions so far? Okay, next up, p-series. I think p-series is relatively easy to spot as well. It's going to be an n raised to an exponent in the denominator. Okay, if it's a variable raised to the exponent in the numerator, then I would just use nth term test, and that should lead me to diverging. Okay, but if it's n to the positive exponent in the denominator, the 5 pi can just go out in front. It's not going to make an impact there. But here, my p-value is clearly less than or equal to 1. If that's the case, then my series diverges by n-term test. If it's greater than 1, then the series converges. If it's like 1.1, then that's enough for a series to converge. Okay, next up, integral test. Integral test, I would say if a problem looks like it could fit into a U substitution form, then I would say integral test would be a good fit. I think sometimes, okay, so I'm forcing you into integral test for the quiz. If you solve this on the AP exam, you may be tempted to want to rely on limit comparison test, which can be faster and easier. But I'm forcing you into integral test here. So this integral test has 3 conditions. So we want to make sure we list out those conditions. You don't have to prove that these conditions are true. You can kind of just do a visual check and convince yourself that these conditions are good to go. So those conditions are positive, decreasing, and continuous. So in this case, positive, because you look at this, all the values here, you don't see any negatives here. Decreasing, right? The limit as n approaches infinity for this does equal to 0. So that shows us this function is decreasing. Denominator degree is higher than the numerator. And it's continuous because you don't see any asymptotes getting in the way. There's no n value that's going to cause an asymptote for this fraction. So no holes, no asymptotes, we're good, continuous. Let me zoom in a little bit. So you would set up your improper integral this way, limit as b approaches infinity, and then you're going to go from your lower bound to b, and set up your u substitution process. In this case, my u value is x squared plus 1. My du over dx is 2x. dx equals du over 2x. Set everything up. I can see that this is going to be a nice fit with natural log. So 1 over u du becomes natural log absolute value u. Replace the u back in terms of x. Plug in my upper bound minus lower bound. And the giveaway is that if my b values in the numerator, typically that's going to indicate this is going to go out to infinity. But if my b values in the denominator, that typically allows for your expression to go to 0. And then if it goes to infinity, it's not a real number. If it's not a real number, then your series will diverge by the integral test. If your integral ends up giving you a real number, then let's say it ends up giving you like 3/2 natural log of 2, then the series converges. But we don't know the sum, okay? We don't know what the sum is. The real number only tells us that the series converged, but the real number is not going to indicate what the sum of the series is. We're not going to have to worry about the sum of an integral or a series by integral test. Okay. Any questions with integral test? Okay, telescoping series. I do want to point this out here because telescoping series can sometimes look like integral test because they both kind of have that fractional form. But here's the way they can tell a telescoping series from the integral test. Telescoping series, your denominator is going to be factorable if it's not already separated. And there's a gap of degree 2 versus degree 0. That's going to be a good fit for telescoping series. Your integral test, if you want to go through your substitution, it's going to be a degree. The gap is going to have to only be off by 1, right? It can't be a gap of 2. Otherwise, it's not going to be an easy use substitution problem. So do you guys see that? Can you spot that distinction between integral test and telescoping? So once you can recognize that this is a telescoping series, we are going to use partial fraction to separate them into individual terms. And the hope is that the individual fractions will end up subtracting from one another, and there's going to be a staggered relationship where they're eventually going to start canceling each other out down the line. And we're going to go through partial fractions. So 3 over n squared minus 1 is the same thing as 3 over n plus 1 times n minus 1. I can split that up into the sum of a over n plus 1 divided by b over n minus 1. We can do the cover-up method. So find a factor on the n plus 1 side, which is -1. Cover up my n plus 1, replace my -1 in for n. I get 3 over -2. So my a is -3/2. Okay. If I want to do the n minus 1 side, I can plug 1 in for my remaining expression. I want to cover up whatever I want to involve. Otherwise, I'm going to get a 0. So 1 in for n. That's 1 plus 1 is 2, 3 over 2. That's my b value. I'm going to rearrange this so that my positive term comes first, followed by my negative term. So 3 over 2n minus 2 over minus 3 over 2n plus 2. And then you're just going through and testing the first 4 or 5 terms. And eventually you're going to see, the staggered relationship where, you'll see a -1/2 and a +1/2, -3/8 and the +3/8. And you're going to start canceling out terms. And once you see a pattern where things start to cancel out, you look at the first few terms and see what remains, and whatever remains is going to be the sum of your series, and we're using telescoping series test to show that the series will converge. Any questions about your quiz tomorrow? Something useful to also know is comparative growth rates. Knowing this relationship can help us with end-term tests. So if you want to write this down, logs grows at the slowest rate, followed by radicals, followed by polynomials, followed by exponential, and then factorial is going to be your fastest growing one. And the nice thing about knowing this relationship is if a higher growing function is divided by a slower one, it's a quick and easy nth term test to show it diverges. So here's a couple of examples. We know this relationship between different families of functions. Radicals will grow faster than your natural log. So this equals infinity, which is not equal to 0. It's a quick nth term test result to show a divergence. Right? It's not as clean if it's flipped around. Flipped around, then it's equal to 0. We got to rely on something else, but this is really helpful, especially if one is faster than the other. So let's say I had n factorial over n cubed plus 1. N factorial is faster than your polynomial. So nth term test diverges. So I think this is really good to know. Can really speed up process down the road, especially if something can be done quickly using nth term test rather than something like ratio test, right? So if we know this relationship, we can save time, especially in the future. So I would like for us to work on do worksheet. I think worksheet 2, we got through the first page, but not the second. All right. So we're going to finish worksheet 2. And you guys also picked up a morning review worksheet. I would like for you to save that for tonight to use as your mock quiz to work through. Or if you want to wait till tomorrow morning, I can work through that with you during the morning review. And then there's also the mixed review. The mixed review has a combination of all the tests. So if you guys can just circle the ones that we're going to be responsible for the quiz, and we can go back and do the ones that are later on. So 1 through 4, 8, 9, 12, 15, 16, 18, 24, and then all the last page, 25 to 31 are all the tests that we're looking at. And cache keys for both of them. So I would like for you to finish worksheet 2 and then start on the mixed review. And then tonight or tomorrow morning, save the morning review to do that last. Also, for worksheet 2, cross off number 13. This is a little too messy here. I won't ask you a problem like that.
I had 44.
Okay.
I today. Okay. Thank you.
Were there any papers I was supposed to get yesterday? Oh, yeah. Oh, listen, you have this spreadsheet. Ten point two or something. Yeah, look for that. If you don't have it, I'll give this to you.
No, it was a different one.
Okay, yeah. Let's just take this one. Again, on worksheet 2, cross off 13. We're not gonna have to worry about this one.
History is relevant for
Okay.
6.
Okay, I'll mark it down. Thank you. Okay, so let me walk around, see your work as you start finishing up worksheet 2. You're done with worksheet 2, then go to your next review worksheet.
I just checked my binder active.
Got it. Okay, great. Thanks.
Also, when you say worksheet 2, what do you look for?
Oh, yeah. So this is worksheet 1. And then worksheet 2 after the key is. Yeah. Again, cross off 13 on worksheet 2. Maybe, yeah. But it won't be ratio test. BC factorial, just break it down, cancel out. Just the.
Factorial is small. Let's just take that.
Yeah, so let's say I had this one here. And this would be n plus 2 times n plus 1 times n, and I just want to keep going until I can match my denominator. Enough for me to pair up and cancel out. And now I'm looking at that. That's my remaining expression. And this would be infinity, so this would diverge my M-sum test.
Okay, so you go until they match.
Until they match, yeah. Yeah.
So,
Yeah, so I'm just gonna ask you for define part B, and then let's see. Part C is only, you can only find the column that's a geometric proposal. You can't just look at it and tell, positive, but you can't imagine positive, that decreasing is the limit of this number is zero. And the decay, continuous is different, than on acetate, that's different way. If average binomial test, if your limit is this, yeah, if one of them's infinity, if it's a real number, then they'll converge. Oh, wait, no, we use integral tests for that. Yeah. Yeah. Right, we should, it doesn't, we're only starting from here, so anything, we'll only get to the right from, so there's no answer, so we're not having issues. But typically, I won't give you ones where we fail on these things. That's the improvements. Yeah, but the numerator's growing at a slower rate, so your limit, this would fail the test. So I would have to split up and look at it. Yeah. If it's anything like that, you got to either do a little comparison or direct comparison, right? You got that. The ones I gave you. Yeah. Yeah, there's a good question about about telescoping series. If once you recognize it's a telescoping series, it's going to converge. You just have to find the sum. So there's no like diverging telescoping series. So once you spot it, then just find the sum. Until you start seeing terms that can cancel it out. And then it's only the first few terms that are going to remain. Added together.
Oh, handouts there. I'll see this. Here, have this one. Okay, bye. Fifth and three. Great. Thank you. Thank you. Mhm. What's that term? If it, if it doesn't equal to zero, then automatic number. So if you 1/2, 1/4, 3.
Anything, and
Yeah, but if it's equal to zero, then it's incomplete. So you got to boost it.
it was just for W.
Yeah, it's only a test for average.
Right.
Oh, sorry, this is part A, sequence, the sequence conversion. But I won't ask you about sequence. I'll ask you about sequence. So basically, the sequence will just be the limit of eight to nine, which is equal to 1/2. But that is not, that's, but the series, it can be numbers. So don't worry about sequence.
There's no sequence for the test.
No sequence for that, but just series, determine convergence and divergence using the proper test, and then finding the sum of the geometric or delta. That's it. So, yeah, we cross off anything dealing with sequence. Yeah, so sequence is what is each term headed towards? The sum would be what's if I were to add up all those terms, is my series won't be converged.
So what's the pattern that the numbers are going into that sequence when I series of
Well, it's easier for sequence to converge.
Yeah.
As long as it's approaching a real number, the sequence converges.
Okay,
But in
yeah.
order for a series to converge,
Yeah, all the
the
numbers.
series has to at least approach zero.
Yeah,
In order for it to have a chance to converge, because you're adding the infinite number to the pairs.
yeah.
So,
So we can,
so
if I'm gonna like initial thing,
the limit
success
of my sequence should approach zero, then it's a n-term test is inclusive, but at least there's a chance that the series will converge.
Yeah.